Hi guys. So today we're going to look at some examples on proof by mathematical induction, right? That's your PMI. And to illustrate the idea behind induction, we have some dominoes set up here. And what really happens when we do induction, we can like knit and say, okay, so we push a domino, it falls, it hits the next domino, that falls, it hits the next domino, and so forth until eventually we push down all our dominoes, right? So, in the context of a proposition or proving a statement, we could say, all right, P of n is true if one, we push the first domino. In other words, we show the base case is true, right? So this is most times it's P of one, sometimes it's not. So we could just put P of B for base, right? And two, once one domino falls, it hits another one and the other one falls. Right? So this is called our inductive step. And it basically says anytime P of K is true, this implies P of K plus 1 is true. Right? So as we go along, our general format for PMI is going to be prove the base case, prove the inductive step. Right? Okay, so let's look at this first example, right? Let P of n be the proposition that 2n plus 1 is strictly less than 2 raised to the power n for all natural numbers greater than or equal to 3. So this is a nice example where our base case actually starts from 3. So let's do the proof. So we first show our base case. So when n is equal to 3, our simplest case, our first domino, what is P of 3? Well, 2 times 3 plus 1 is less than 2 raised to the third power, which is 2 times 3 is 6 plus 1, 7 less than 8. And this is true. So, therefore, or hence, P of 3 is true. Nice. So we pushed our first domino, right? So because that works, we could kind of assume, and let's say, okay, if it works for our first case, let's assume it works for some arbitrary case, right? So this is your inductive hypothesis, which says assume P of K is true. So what does P of K give us? Well, anywhere we see N, we're just gonna write K. So 2K plus 1 is strictly less than 2K, where K is, of course, a natural greater than or equal to 3, right? Because K is some number between our base case and our nth case, right? So what we need to do now is we need to prove the inductive step. So we need to show anytime P of K is true, P of K plus 1 is also true. So we consider when n is equal to K plus 1. So what is P of K plus 1? P of K plus 1 is 2 times K plus 1 is less than 2 to the power K plus 1. So this is a statement that we need to show is true. So, all right, so this is our proving our inductive step now. Inductive step. So let's start with the left-hand side, right? So let's start with 2 times K plus 1 plus 1. When P of K is true, can we show this is in fact less than 2 to the power K plus 1? Well, let's see, right? So let's expand it first. So we could expand the bracket, we get 2K plus 2 plus 1. And what I'm actually going to do is I'm going to use the commutative law on addition to write this as 2K plus 1 plus 2. So why did I do that? Well, if you look at the inductive hypothesis, our inductive hypothesis says 2k plus 1 is less than 2 to the k. And look, I have 2k plus 1 here. So that means I could just substitute this into the equation and I could say then, well, 2k plus 1 is less than 2 to the k. So 2k plus 1 plus 2 must be less than 2k plus 2. Right? And this comes from our inductive hypothesis. Right. So where do we go from here now? So we know that 2 is less than 2 to the k when k is greater than or equal to 3. So this entire statement here is simply less than 2 to the k plus 2 to the k. Since 2 is less than 2 to the k when k is greater than or equal to 3. Now, what did I do here? How did I go from this line to the next line? So let's look at a numerical example just to kind of give you all the idea of what went on here. If I have 2, 2 is clearly less than 8, right? So what if I had x plus 2 now? X plus 2 is definitely less than x plus 8, since 2 is less than 8. So if k now is greater than or equal to 3, our possible values of 2 to the k, starting from 3, is 2 to the 3, which is 8, 2 to the 4, which is 16, 2 to the 5, which is 32, etc., etc., right? And these are all greater than 2. So what I'm saying, now let's write instead of x, we have 2 to the power k. 2 to the power k plus 2 is less than 2 to the power k plus 2 to the k, right? Because 2 is less than 8, is less than 16, is less than 32, and so forth, and so forth, right? So that is the reasoning behind this next step here, right? So and now, of course, 2 to the k, those are like terms, so we could kind of like x plus x is 2x, so 2 to the k plus 2 to the k is, of course, equal now to 2 times 2 to the k. And why could we do this? Because we are not dealing with equality. The statement we need to show is an inequality, it's less than. So we could technically add any arbitrarily large term to ensure our next line is greater than the line before it. What does that mean? We don't need to preserve equality. So we could say that 2k plus 1 is definitely less than 2 to the k. 2 is definitely less than 2 to the k. And now we kind of come back, well, this line is equal to this line, right? So this first line here is still less than this line here, right? So we're good. So using our laws of indices now, what is 2 times 2 to the k? 2 to the k plus 1. So what do we have? We have 2 times k plus 1 plus 1 is less than 2 to the k plus 1. And that is exactly p of k plus 1. That is exactly what we needed to show. So we can say now, hence, p of k plus 1 is true whenever p of k is true. So by PMI, what was our proposition? It was 2 times n plus 1 is strictly less than 2 to the n for all natural numbers greater than or equal to 3. So the result is proven. Okay, so this next example is a divisibility one, right? So we have Pn is the proposition that 7 divides 2 to the power 3n minus 1 for all natural number. So it's the same format. We need to prove our base case first. And now we're dealing with n is a natural number, no restriction. So natural numbers, the counted numbers, we need to start from n is equal to 1. What happens? 7 should divide 2 to the 3 minus 1, which means 7 should divide 8 minus 1, which means 7 should divide 7. And this is true, because 7 divided by 7 is just 1. So hence, P of 1 is true. Okay, great. So our base case is true. So let's assume it is true for some random natural, right? Arbitrary natural. So the inductive hypothesis, we assume P of k is true. So that would mean that when n is k, this proposition here, 7 divides 2 to the 3k minus 1. But what I'm going to do is I'll use our definition of divisibility, and I'm going to write, therefore, so I'll write 2 to the 3k minus 1 is equal to 7 times some integer a, right? So if this is divisible by 7, we could write it as the product of 7 and some integer a. And what I'll do is I'll actually make 2 to the 3k the subject of the formula. And you'll see why I did that just now. Right. So we assume P of k is true. This is P of k. And we want to consider when n is equal to k plus 1. So what does that give? P of k plus 1, which is 2 to the power 3 k plus 1 minus 1 is divisible by 7. This is what we need to show is true. Okay, so let's see if this is possible. Let's take here. So we are now going to prove the inductive step. Right, so we have 2 to the power 3 k plus 1 minus 1. So what is this? Let's expand the exponent bracket, right? So 2 to the power 3k plus 3 minus 1. On laws of indices, we could write this as 2 to the 3k times 2 to the 3 minus 1. Why did I write this like this? And why did I write our inductive hypothesis like this? Well, 2 to the 3k is equal to 7a plus 1. So I could just make a substitution here now, and I could write this is 7a plus 1 times 2 to the 3 minus 1 by our inductive hypothesis. Right. So where are we now? Let's see. Let's expand this. 2 to the 3 is obviously 8. 7 times 8 is 56a plus 1 times 8 is 8 minus 1. This is 56a plus 8 minus 1 is plus 7. Could we factor out 7? Yes, we can. We have 8a plus 1. So here's the question. Does 7 divide this? Well, you see, 8a plus 1 is an integer because integers are closed under multiplication and addition. So, since 7 divides 7 into 8a plus 1, P of k plus 1 is true whenever P of k is true. So, by principle of mathematical induction, our conclusion is that 7 divides 2 to the 3n minus 1 for all natural numbers n. And that's the proof. All right. So our final example now is a series, right? So we want to prove the proposition that the sum of r times r plus 1 is equal to 1/3 n times n plus 1 times n plus 2 for all natural numbers. What are we adding up here? What is our summation? We are summing terms of the form r into r plus 1. So what is our first term? It's when r is 1. So 1 into 1 plus 1 is 2. What's our next term? When r is 2, 2 into 2 plus 1, 2 times 3 is 6. 3 times 4 is 12. 4 times 5, 20. So forth and so forth. And each term is of the form r into r plus 1, right? And we go all the way up to n. So any term that we put in this series here looks like this. So let's actually go ahead with the proof now and see how that could help us. So we need to show our base case, same format, right? So natural numbers, counted numbers, when n is equal to 1, what do we have? What is the left-hand side here? The left-hand side is going to be the sum of the first term, which is actually just 2, as we wrote out here. The right-hand side, we substitute n as 1. We have 1/3 to 1 to 1 plus 1 to 1 plus 2. That is 1/3 times 1 times 2 times 3. That is 2. So of course, since the left-hand side equals the right-hand side, hence P of 1 is true. Great. Base case is true. So let's go through with the inductive hypothesis. So our inductive hypothesis, we assume P of K is true. So our inductive hypothesis so inductive hypothesis assume P of K is true. All right, so what do we have then? It means anywhere we see n in our original proposition, we're going to put k instead. So this implies the sum from r is equal to 1 to k of r into r plus 1 is equal to 1/3 k times k plus 1 times k plus 2. And of course, k is a natural number. So if we assume this is true, can we show, consider when n is equal to k plus 1. What is our P of k plus 1? So P of k plus 1 will be given by the sum from r is equal to 1 to k plus 1. So now anywhere we see n, we are writing k plus 1, right? 1/3. Instead of k, we have k plus 1. Instead of k plus 1, we have k plus 1 plus 1, which is k plus 2. And then k plus 1 plus 2 is k plus 3. So this is what we need to prove. So can we use P of k to show this is true? So we can write the summation r into r plus 1 from 1 to k plus 1 is actually equal to the summation r into plus 1 r is 1 to k plus the k plus 1th term, right? Because this is a summation. So the summation of the first tree is the first plus the second plus the third. The summation of the first k is the first plus the second plus the third all the way up to the k. So the summation of the kth plus 1 is the first plus the second to the third up to the kth plus the kth plus 1. So from our inductive hypothesis, we have an expression for this. That's right here. So this is equal to 1 over 3 k into k plus 1 into k plus 2 plus the k plus 1th term, right? And how do we get this? This came directly from our inductive hypothesis. Nice. So what is the k plus 1th term? Is it just k plus 1? No, because back up here, I was explaining any term is of this general form. So the k plus 1th term is k plus 1 into k plus 1 plus 1. Anywhere I see r, I'll put k plus 1. So this is equal to 1/3 k into k plus 1, k plus 2, plus k plus 1 into k plus 1 plus 1. What do we have? We have 1/3 k into k plus 1 into k plus 2 plus k plus 1 times k plus 1 plus 1 is, of course, k plus 2. Right. So let's factor out the common factor here. So the common factor is k plus 1 times k plus 2. And what are we left with? We have 1/3 k plus 1. Nice. Let's pull 1/3 out of this. So if we pull 1/3 out of this, we have 1/3 k plus 1, k plus 2. And what's left in here? We take out 1/3, so we have k plus 1 divided by 1/3 is 1 times 3, which is 3. Does this look familiar? This is exactly p of k plus 1. So we just took p of k and showed p of k plus 1. So hence, p of k plus 1 is true whenever p of k is true. So by principle of mathematical induction, the summation from r is equal to 1 to n of r into r plus 1 is equal to 1/3 n into n plus 1 to n plus 2 all naturals n. And that's the proof. So I hope this helps. And if there are any questions, you can, of course, email me, right? But that is it for this tutorial. Okay, bye.